In this lesson, we're going to be looking at the derivative of logarithmic functions. Let's look at finding the derivative of the function log base A of x. We're going to use a technique very similar to the technique we used when we found the derivative of inverse trigonometric functions. What we are going to do is we are going to rewrite this function y equals log base A of x in its equivalent exponential form. Now the equivalent exponential form is a to the y equals x. And now we'll take the derivative implicitly. One of the rules that we need to remember is if we take the derivative of, let's say, a to the x, we know the derivative is ln of a times a to the x. Now applying that rule, we know that y is some function of x, so we would have to apply the chain rule. So the derivative of a to the y, looking at our results here, we would have ln of a times a to the y. But now y is some function of x, so we would have to apply the chain rule times y prime. And then the derivative of x is 1. Isolating y prime, we'd have 1 all over ln of a times a to the y. We want this as a function of x. That's our derivative, but we want it as a function of x. So what we're going to do is we're going to look at this a to the y, and up here we say a to the y equals x. So we'll make that replacement, and our derivative, we don't want a to the x. That is the derivative of the log base A of x. Let's do the same with the function ln of x. Now we know ln of x, typically we just write it as y equals ln of x. However, I just wrote it to remind us of the base for the ln is e. So if we switch this into the equivalent exponential form, we'd have e to the y equals x. Taking the derivative of the left-hand side, the derivative of e to the y times y prime, derivative of x is 1. Solving for y prime, 1 all over e to the y. And we would change this back into terms of x by using this relationship here. So we would get 1 all over x. There's the derivative of the natural log of x. An example, differentiate ln of x cubed minus 2. I'm going to show this using f of x and g of x, and then I will also show it using the other technique where we let u equal the inside function and then rewrite y in terms of u. So first off, let's identify our inside function, which would be our g of x. So g of x equals x cubed minus 2. Since we are working with a composite function, we see the inside function is x cubed minus 2. And the outside function, our f of x, would be ln of x. F prime of x, we just found, is 1 over x. So f prime of g of x. Now we're going to take our f prime of x, and wherever we see an x, we're going to replace it with g of x to get our f prime of g of x. So we'd have 1 divided by x cubed minus 2. And we know we have to multiply that times our g prime of x, and g prime of x is 3x squared. So just a quick review, when we're taking the derivative of a composite function f of g of x, we know the derivative is f prime of g of x times g prime of x. So our f prime of g of x is right here. So that is our 1 all divided by x cubed minus 2 times g prime of x, which is here, which is 3x squared. So that is our derivative of our function, ln of x cubed minus 2. And if we simplify it a little bit, we have found the derivative of ln of x cubed minus 2. Now the next technique I'm going to show is the technique where we let u be the inside function and y equals a function of u. So there's our inside function, x cubed minus 2. So we'd have the outside function in terms of u would be ln of u. Now we just take the derivative of each one of these and then multiply them together. And we want this to be a function of x, and we defined u to be x cubed minus 3. So we would get our derivative. Another example. Let's find the derivative of the natural log of the cosine of x. Again, I'm going to show you both techniques. So g of x would be our inside function, which would be the cosine of x. F of x is going to be ln of x. So we would find our f prime of x is 1 over x, and f prime of g of x. Now we're going to replace our x here with the cosine of x. That's what g of x is. So we'd have 1 all over the cosine of x. Then we need to find our g prime of x, and the derivative of cosine is negative sine of x. So we would multiply these two together, this one and this one, to get our derivative. So the derivative of our ln of the cosine of x we found to be this one times this one. So we'd have negative sine of x divided by cosine of x. And if we used our knowledge of trigonometry, we know sine divided by cosine is tangent, and then that would be negative tangent x. Now the other technique, identify our inside function as cosine of x. Then we have y equals ln of u, derivative of each, multiplied together, and we make our replacement with u equals cosine of x, and we get our negative tangent x. You may have seen from the last two examples that when we take the derivative of a natural log and then the argument is some function of x, could you generalize what that is? What have we been getting? Well, we end up with f prime of x over f of x. And that works whenever we're taking the derivative of the natural log of some function of x. It's just f prime of x divided by f of x, where f of x is that inside function. I could have named that g of x also, because we usually do identify our inside function as g of x, but it doesn't really matter. Okay, differentiate. Now here, it appears we have the composition of three functions. However, I'm going to still write this as our inside function, g of x. I'm just going to identify that as ln of x squared minus 1. And then our f of x would be the square root of x. Taking the derivative of f of x, we know that is 1 all over 2 square roots of x. Just remember, x to the 1/2 is the same as the square root of x, so you'd bring your 1/2 down in front, subtract 1, so you'd have 1/2 x to the negative 1/2. Then we're going to find f prime of g of x. So that would be 1 all over 2. Now I'm going to replace the x with g of x. So we'd have the square root of ln of x squared minus 1. And then finding our g prime of x, we know this one is the inside function, the derivative of the inside function over that inside function. So if I said u is the inside function, which would be x squared minus 1, the pen's not working up there, so let me do it down here. If u equals the inside function, which would be x squared minus 1, the derivative then would be 2x. So we could write g prime of x as u prime over u, 2x all over x squared minus 1. Now multiplying our f prime of g of x times our g prime of x, we would have 1 all over 2 square roots of the ln of x squared minus 1 times 2x all over x squared minus 1. And we could actually simplify this a little bit. We could reduce the 2's and then write x over. So we would reduce our 2's and we would have x divided by, we'd have the square root of ln of x squared minus 1 times our x squared minus 1. The other technique, here we're going to recognize this is the composition of three functions. So we're going to start out with the innermost function as v, which would be x squared minus 1. Then working outward, the next function would be ln of x squared minus 1, but x squared minus 1 is v, so we'd have ln of v. Then the outside function is the square root function, so we would have y equals u to the 1/2. Now we take the derivative of each one of these and we multiply these together and we replace u and v back into terms of x. So we make our substitutions and there's our derivative. We could again reduce those 2's. Differentiate log base 8 of 5 minus cosine of x. Inside function, g of x equals 5 minus cosine of x. F of x equals log base 8 of x. Now f prime of x. Now if you think about, we did this a couple of slides back. We looked at finding the derivative of this by rewriting it in exponential form, taking the derivative implicitly, and then we found y prime equals ln of 8 times 8 to the y, but then 8 to the y, if you look back up here, is equal to x. So that's our derivative here. 1 all over ln of 8 times x, and then f prime of g of x will replace x with, this is g of x here, so we're going to replace x with 5 minus cosine x, and then g prime of x, derivative of 5 goes to 0, derivative of cosine of x is negative sign, so we'd have a negative sign, which is positive sine x. So now we can multiply those together, and I'm just going to put sine of x in the numerator, all divided by our natural log of 8 times 5 minus cosine of x. And this is our derivative. Using the other technique, we would have the inside function is 5 minus cosine of x, y equals log base 8 of u. Take the derivative of both of those, multiply them together, and we get our derivative. Find the derivative of the natural log of x plus 1 divided by the square root of x minus 2. Now this one we may be able to rewrite this one before we find the derivative. Could we rewrite this one as the natural log of x plus 1 minus the natural log of the square root of x minus 2 using properties of logarithms? So now we're going to try to find the derivative of this function. And we could still rewrite ln of the square root of x minus 2 as ln of x minus 2 to the 1/2 and bring the 1/2 down in front of the natural log. So it would look like we would have the natural log of x plus 1. Now this could be written as ln of x minus 2 to the 1/2 power. Now we could bring that 1/2 down in front using properties of logarithms. So we would have this. We can take the derivative of these separately now. So the first one here, we know the derivative is going to be the derivative of the inside function over that function. So u would be the inside function, and the derivative would just be 1. So u prime over u would equal 1 all over x plus 1. Likewise with the second term. Now this 1/2 is just a coefficient, so we can find the derivative of natural log of x minus 2 and then multiply it by 1/2. And again, if we let u be the inside function, u prime is just going to be 1. So u prime over u would equal 1 all over x minus 2. And then we would multiply that by 1/2. So our derivative would be our x plus 1 over x plus 1 minus 1/2 times 1 all over x minus 2. And this all comes about remembering that the derivative of the natural log of a g of x would be g prime of x divided by g of x. And that's the rule we applied here to find the derivatives. Now the other technique, if you just looked at this problem and said, well, I see the inside function as x plus 1 divided by the square root of x minus 2, and then the outside function is ln of 2, we're going to have to apply the quotient rule when we take the derivative, du dx. And then dy du, and here this is du dx, du dx. And then multiplying those together to get our dy dx. You see there's going to be a little bit of simplifying to do. And we would get our derivative. Now this one, we do have the common denominator, so if you wanted to double check with the last technique we used, just finding our common denominators and then combining like terms in the numerator, we'll get the same answer. Here's a graph of the function that we just worked with and the derivative of its function. So just analyze that a little bit. Look at the slope of the tangent lines to the function. You can see they'd be very negative when x is very close to 2 from the right, they'd be very negative, and then as x got larger and larger and larger, you can see the slope of the tangent lines would be approaching 0. Okay, we're supposed to find the derivative of the natural log of the absolute value of x. Let's break this up into a piecewise function and see if we can generalize our results. We know that the ln of x would be the function we would use if x is greater than 0, and ln of negative x is the function we'd use if x is less than 0. Let's take the derivative of each one of these individually. So if we take the derivative of the natural log of x, we get 1 over x when x is greater than 0. And the derivative of the natural log of negative x, we have to remember to apply the chain rule here. Because if we let g of x equal negative x, g prime of x would equal negative 1. Our f of x would be ln of x. F prime of x equals 1 over x, and f prime of g of x would be 1 all over negative x. When we multiplied these two together, we would get negative 1 times 1 all over negative x, which is just 1 over x. Okay, so we can see we get 1 over x regardless if x is greater than 0 or if x is less than 0. So therefore, we could generalize our results for all x, the derivative of the natural log of the absolute value of x equals x. That's the end of part 1.